Welcome to another edition of Physics at Home with me, Mr. Garrett, and a child's shoe. Okay, so in this lesson we're going to be looking at pressure. Now you will probably be familiar with the idea of pressure, and if you're thinking about, well, what does pressure mean to you, it possibly could be if you have a bottle of Coke and you were to shake up the bottle of Coke, it would become pressurized. There would be a build-up of pressure that when you release the lid you would get there. And you could blow up a balloon and it would be under pressure if you popped it. But really what we're going to do, we're going to look at pressure in terms of the force that is applied to something. Let me give you a couple of examples of pressure. And so if we were to have, hang on a second, I'll go get something. We have a nail. And so you can see with this nail, and obviously you immediately recognize that it's a nail. You'll see that it has a sharp end and a broad flat head. And so this typifies what we're talking about with pressure. If you were to try and take the nail and then force it into the table or the jotter or whatever, then that's what it's designed for. But the way that it achieves this is by having a very, very small head or tip, that when you apply the force onto this, then that force is transmitted through the nail. But the key is that because it has such a small point of contact with the book, then it can go through and it can pierce through whatever material it's going into. And so when we're talking about pressure, we're talking that there's a couple of things that are important there. First of all, that you have the force. So the force that you apply to it, the greater the force will obviously be the greater the pressure that is applied, but also it's the surface area that is in contact with whatever it is. And so let's look at the learning intentions, and then we'll carry on with what we're doing. So in this here we have gas laws in the kinetic model 16.1 and 16.2, and that's saying I can explain that pressure is the force per unit area exerted on the surface, and then I'm able to use a formula P equals F over A to calculate pressure, force and area. Pretty simple, pretty short. All we have is this idea of force per unit area. And so we have the pressure, which is defined as the force per unit area, and we can see here at the top of the course notes on page 10 that pressure is defined as force per unit area. That's what we have been saying. Pressure is measured in something called the Pascal, PA for short, capital P, small a. And similarly, as we've defined other units and quantities that we have to make sure that we differentiate between pressure, which is force per area, and then we can define what we call the Pascal, so the unit of pressure, and that would be defined as the number of newtons per meter squared. Meter squared is obviously the unit for area, and newtons the unit for force. We have our formula, and the formula really is just a mathematical version of this, the force per unit area, so force divided by the area. And that's really it. That is in a nutshell what we have for pressure. Now, if we're talking about the pressure of us standing on something, and here is where shoe comes in. We'll get to that in a little bit. But if we're standing on a surface, and so here we go, I'm going to have somebody with very odd legs, and they are standing on a surface. Now the pressure is going to be at the point of contact with whatever they're standing on. So if they're standing on the floor, then the pressure will be at the point of contact with the soles of their shoes and the floor itself. And so we have a force. Now where is this force coming from? So this force is coming from gravity. So the force of gravity, which is equal to weight, which is going to be mass times gravitational field strength, or mg. If they're standing on Earth, then our g is going to be 9.8. And so we would have there. And the area, well, the area is going to be the contact that they make with the floor. So the surface area in contact with the floor, that would change, well, first of all, depending on what type of shoes you're wearing. If you can imagine that our person here is wearing trainers or sneakers, so you can sneak around, then we would have a sort of fairly broad foot-shaped sneaker shoe pattern like this. We may have like complicated it up and have some sort of treads in there, but you know what I'm talking about. All of the sort of contact patch of the sole of the shoe, the bits that are in contact with the floor, would all add up to make the total amount of area that was in contact. Now if you're standing, usually you would stand using two legs, then this would be area of one shoe times 2. And so you work at the area. If you're just looking at an object, a simple object such as a cube that was sitting on the floor, or sitting on a surface, sitting on a table, whatever, then you would be able to, if I draw, I'm sure there'll be a name for this, a projection of some sort, and then there we go, the area that is in contact with the surface would be like this, and we would just have our length times breadth, and so the area here is equal to length times breadth. And this would be measured in, well, we would really have to measure this in meters to get, because remember our definition of area is in meters. So squared. So that needs to be whatever it is. If you have 20 centimeters by 20 centimeters, you would need to convert that then into 0.2 times 0.2 to get your area. Okay, so now, well, let's see how this would work in real life, and this is why I have a small shoe. And I got a small shoe rather than one of my own shoes or anything, simply because I can, and it makes it really, really easy, because if I'm going to get, hang on, if I'm going to get this, a sheet of A4 paper, then my child's shoe fits really, really easily on my A4 piece of paper. Simple. Now, if I want to find out the pressure that the owner of this shoe exerts when she's walking around, then we just need to figure out the area if we measure our mass, then we can figure out the force, her weight force that she is applying over that area, and we can get the pressure. So, well, let's go ahead and do that now. Well, what we're actually going to do, we're going to do something way better. We have a real foot now, and then we're just going to try and draw around this. I'm sorry if it's tickly. And so there we're going to draw around. Okay, there we go. Okay, so we now have the outline of a foot, and what we need to do is we're going to, well, each of these squares here, this is 1/2 centimeter, so this would be 1 centimeter. Now, this is the outline of the foot, and all we're going to do is, well, what I'm going to do, I'm going to count up all of these little squares, and I'm going to figure out the area of my assistant's foot. I'll be back in probably a few minutes once I've done that. Okay, still going. And so what I've done is I've just blocked off certain amounts of area, and then when I have areas like this that are not complete full segments, I've approximated that this little bit here added on to that bit there would make up one whole centimeter squared. And so I'll finish this off, and I'll add up everything, and then I'll come up with an area for you. So I have come up with 71.5 centimeters squared. Now, I know only a few minutes ago I said that the area that you measure must be in meters squared, and so part of the reason why I'm going through this laborious process is to actually show you how we get from centimeters squared, or even indeed millimeters squared, into meters squared. So if we have 1 centimeter, and so 1 centimeter square would be 1 centimeter times 1 centimeter, and that's just 1 times 1, which is equal to 1 centimeter squared. Now, if we were to look at what this is in meters squared, and so 1 centimeter in a meter is 0.01 meters by 0.01 meters, and that is going to work out as 0.01 times 0.01, and that will give us, no, centimeter squared is going to equal 1 times 10 to the minus 4 meters squared. And so that is our conversion between centimeters squared into meters squared. Now, if we're going to look at 1 millimeter squared, so we've got 1 millimeter by 1 millimeter, that's 1 millimeter times 1 millimeter, we're going to have 1 millimeter squared. Now, that 1 millimeter is going to be 0.001 meters times 0.001 meters again. And that's going to work out as 1 times 10 to the minus 6 meters squared. Okay, right, so we have conversions for centimeters to meters. Okay, so we now have our conversion scales um, for centimeters. So 1 centimeter squared is 1 times 10 to the minus 4 meters squared. We have 71.5 centimeters squared. So to convert that into meters squared, we're just going to multiply that. 71.5 times 1 times 10 to the minus 4, 1 times 10 to the minus 4. Really simply, that's just going to give me 71.5 times 10 to the minus 4 meters squared. So that is the area. Now that is the area of 1 foot. If I was going to do this, and assuming that my daughter's feet are the same size, then I'm just going to multiply this by 2. And so that will be 143 times 10 to the minus 4 meters squared. Now all the maths teachers and the maths people in the world are freaking out now that I'm going to leave this in this form. I could, if I really wanted to, go 1, 2, and give you 1.43 times 10 to the minus 2, but I don't want to. I'm going to leave it at that, maybe just to be obstinate. Okay, so for 2 feet, we have an area of 143 times 10 to the minus 4 meters squared. All right, cool. Now, mass of child. Should we call her child? Yes, mass of child. So mass of child, I have it on good authority that she is 22 kilograms. So 22 kilogram child standing with her little feet there. So let's work out the weight of the child. And so W equals mg. We have 22 times 9.8. And that is 215.6. 215.6. This will be newtons, remember, it's force. And so we now have an area, we have a force, and we have pressure. So finally, pressure, P, big P, is equal to F over A. Force over area. The force, 215.6. Area, if we remember, was 143 times 10 to the minus 4. 143 times 10 to the minus 4. And that all together is going to give me something big and horrible. 15076. So 15,076.9. So I'm going to round this. Let's get this properly rounded. Bring my inner maths teacher out and put it in proper scientific notation. So let's go 1.5, and then we've got 1, 2, 3, 4. 1.5 times 10 to the power of 4 pascals. So that is the pressure that child exerts on the floor when she is walking. In real life, in that this isn't going to really be the case, because it's going to be a bit more complex than that. She's not going to stand with an equal pressure throughout all of her feet. There'll be more in her heel and more across the ball of her feet, some with her toes, but then a lot less with the arch of her foot. And so, but really what I was trying to do is to try and get you to understand conversions of areas, like centimetres into meters, and metre squared, centimetre squared, and just as a wee demonstration of how you would work out the pressure of something or somebody sitting on a surface on Earth. Yeah. Okay. Right. I think that's pretty much us for pressure. It's not a really major thing. There's not a lot in it. As you saw from the learning outcomes, you need to be able to define that pressure is the force per unit area, and you need to be able to use the formula to work out stuff. And so we have that there. We've got the worked example there. There's another worked example there, and then there's some practice problems which you can work your way through as well. Okay, well, thanks for watching, and I hope you've enjoyed it, and I'll see you again soon. Okay, bye.